grade 10s and welcome to this week's lesson on properties of quadrilaterals. Now you've been working with quadrilaterals for quite a while. You've been naming squares, kites, and sometimes they're called diamonds, but that's really only in junior school, and all sorts of rectangles, all sorts of things like that. Now the common characteristic between all of these quadrilaterals is that each one has 4 sides as well as 4 vertices. Now vertices are the corners. It's where 2 lines come together at a point. A vertex is the singular form of the word. So if I have 1 corner, I have 1 vertex. If I have 2 corners, I have 2 vertices. Terminology like that becomes quite important when we're talking about things in Euclidean geometry. It's so that we can all understand what we're all saying. You'll remember that we've spoken about supplementary adjacent angles. If you don't know what supplementary means, you're going to struggle to understand what your teacher's saying or what the question's asking for you. So make sure that you keep up to date with the terminology as we're going on. Maybe you've made a little list and you're writing down the definitions next to each thing, and try and use these words in everyday context so that you can get used to what they mean and how to use them. Okay, now on that note of terminology, let's take a look at our first slide. And I'm going to give you 1 minute now to go through the following words and write down what you think parallel means, what bisect means, and what diagonal means. Okay, you've got a minute. Were you able to remember all of those terms? How do you think you did? Now these are just 3 words. The rest of the words we're going to be talking about as we define the different types of quadrilaterals. Yes, there are different types, and yes, it is important to know the differences, just so that you can treat them in the right way. Okay, let's look at the definitions that I have. The first one is for parallel, and it says 2 lines that remain the same distance apart from each other at any point. I prefer to think of it as 2 lines that will never ever touch each other. So it doesn't matter how far we draw these lines, they will always be exactly the same distance apart and never ever touch. It's quite sad. Look, same distance there and same distance there. That line is parallel to that line. So there we go. Now bisect means to divide in half. You could have angles that are bisected. You can have lines that are bisected. If I have an angle here and then I want to bisect it, I'm going to draw a line right through the middle of the angle so that it is the same size on both sides. But of course I haven't done that very well, so let's tap on it so that we get it to look like roughly the same size. You see? So in other words, if we go back to our colors, if this was 30 degrees, then this would be 30 degrees as well, and that line would bisect the angle. And as I said, lines can also be bisected. So let's put in a little line over there, free hand. And if I were to tell you that this side is equals to that side, then that line has bisected this whole line over here. Okay, so bisect means to divide in half. Now diagonal is a line drawn from one vertex to another. And we're going to see a lot of these as we go through the definitions of quadrilaterals. But let's say we have a parallelogram. Remember, a parallelogram has four sides, well, two pairs of sides that are parallel to each other. So that's parallel to that, and that is parallel to that. A vertex would be, well, a vertex would be the corner, but a diagonal would be the line that's drawn from one side to the other. Now grade 10s, it's really easy to remember how the shapes look. It's really easy to identify a rectangle and a square and a rhombus and a parallelogram. What people struggle with most is actually the properties of the diagonals. And that's where most of your questions in exams will come in. They'll ask you to identify a type of quadrilateral, but they'll only give you the properties of the diagonals of the quadrilateral. I'm going to show you how it's easier to remember these different properties. I'm not very good at remembering things, so I'm going to show you my tricks with this. Okay, so now we're going to look at a couple of diagrams of the different ones. And I think the most obvious one to start off with is a parallelogram. Now a parallelogram also has four sides. Look, 1, 2, 3, and 4. It also has four angles. We've got A, B, C, and D. Now in a parallelogram, our opposite sides are equal to each other. Let's just scroll up a little so that you can actually see. In other words, line DC has the same length as line AB. And line AD has the same length as CB. But as I said, that's not the difficult thing to remember. If we label this point in the middle, let's label it E. We know that the diagonals bisect each other, which means that AE has the same length as EC. There we go. So that over there is the same length as that side over there. And we also know that DE has the same length as EB. Why? Because diagonals bisect each other. We can also tell that this angle over here is equal to that, but that's just because they are vertically opposite for no other reason. Now, grade 10s. People often wonder, why is this so? Especially in Euclidean geometry. People keep going, but why do the diagonals bisect each other? And then I tell this story about how some things just are the way they are. If you draw any parallelogram, and you can try this now, or try it at home, or whatever. You draw a parallelogram so that the opposite sides are equal in length. Then the opposite sides will automatically be parallel. Or if you draw opposite sides that are parallel, the opposite sides will also automatically be equal in length. It's something we've noticed as things have gone along, as we played with the shapes. So these things are always true. Now, with the diagonals, as you draw your parallelograms of different sizes, draw the diagonals in and measure them. And what you'll see is that the diagonals will always bisect each other. So they'll always cut each other in half. The diagonals won't have the same length as each other. You'll have one that's shorter than the other. But they will cut each other right down the center of each other. And those are really the important things to remember with a parallelogram. You also need to remember that the opposite angles are equal to each other, but the rest of it you can just kind of figure out. Okay, now I said I was going to show you an easy way to remember these things, or an easier way. And the easier way for me is to remember how shapes are different from each other. So I'm going to draw a parallelogram quickly over here. A normal parallelogram. And hopefully this is equal enough. But there we go. Now, if I want to change this, I have a number of different ways I could change it. I could decide, no, I want to, instead of having those funny angles, I'm going to make all my angles right angles. So all I've done is taken my parallelogram and given it all right angles. All of my distances or my lengths are exactly the same as they were. But I've taken it from its squashed position and I've made it now straight up. And what kind of shape is it when it's straight up like that? It's kind of like a rectangle, isn't it? Now, a rectangle's properties are very similar to a parallelogram's properties, except a rectangle has right angles. The opposite sides are still equal to each other, and they're still parallel to each other. The diagonals, they still bisect each other, but the diagonals are also equal to each other on top of that. So there are the two differences. The diagonals are equal to each other, and the vertices are right angles. Now, if I wanted to change a rectangle in one direction, I could either squash it again and make it a parallelogram, or I could take the rectangle and squeeze it to turn it into a square. Now, a square has right angles, its opposite sides are equal to each other, and all of the sides are actually equal to each other. So it's like an additional thing. All right angles, the diagonals are equal to each other, but the diagonals also meet at 90 degrees. Let's take a look at some of these other changes. So I'm going to scroll forward and we're onto a rectangle. Now you'll remember what I just said. A rectangle is kind of like a parallelogram that's been made straight. So I've drawn that line skew over there. So let's just, let's move it over there. So there was the parallelogram, and then I wiggled it around a little so that I now had right angles. All of my lines were still the same length. So my diagonals have changed in length, and you'll see that they're also equal to each other now. So DB is the same length as CA. And look, they still bisect each other. To the center is the same length as C to the center. And our opposite sides are still equal in length, but the right angle is new. So that's new. And the diagonals being the same length is new. Diagonals. And I'm pretending I know how to spell diagonals. I do, but I'm just hitting a blank right now. Okay, now if we go to a rhombus, what does this shape kind of remind you of? And I'm going to draw one right now. What shape is this? It's a square. It is a square. So a rhombus is actually a square that has been squashed. If I were to take that and just squash it over to that direction, so that, it's a terribly drawn rhombus, but you get the idea. Have the lengths of the sides changed? Well, if I had drawn it accurately, no, they wouldn't have. This would still be the same length as that and that and that. but the angles have changed. In a rhombus, they are not 90 degrees. So they're not right angles or not perpendicular. There's a lovely symbol. But did you notice that the diagonals bisect each other, even though they're not equal, and they bisect at a right angle, so they're perpendicular to each other? Okay, opposite sides are equal, and they are equal to each other. So other than that, it's all good. Now the square, how is this different from a rhombus? Well, a rhombus had angles that weren't equal to 90 degrees. A square has angles that are equal to 90 degrees. And because they're equal to 90 degrees, our diagonals are equal in length. I suppose that means we could say if the angles are 90 degrees, then the diagonals are equal to in length. The diagonals, you see I can spell diagonals, are equal in length. It's a nice conclusion. Now, grade 10s, while you take a break, I'd like you to redraw the parallelogram, the rhombus, the square, and the rectangle. But instead of drawing down all of the characteristics, I want you to try and jot down what makes each quadrilateral different to each other. I've got my idea, and when we come back, I'll check if it's the same as yours. See you just now. Okay, grade 10s, how was your break? While you were busy, and I was also busy, I drew some of the quadrilaterals. In fact, I drew the 4 that we were talking about. So we're going to look now at the screen. And obviously, this one is a square. And how do I know that? Because the lengths are equal to each other. Now, if I squash the square, the lengths are going to stay the same, but the angles will change. So this was 90 degrees, but now, who knows, it could be 110 degrees. Well, I don't know. Maybe it's 110. If that's 110, that means that this is 70. How do I know that? Because these are opposite angles in a rhombus, which means they're equal to each other. And angles of quadrilaterals add up to 360, which means those would be equal to each other. Also, they're co-interior angles. There's the C, co-interior. So a rhombus is a squashed square. Rhombus is a squashed square. And that means it has all of the same characteristics as a square, except for the things that are affected by the squash. And the things that are affected by the squash are the angles and then the lengths of the diagonals. But the diagonals are still going to meet at 90 degrees. So they're still perpendicular to each other. Also, they're still going to bisect each other. Okay, so what is the difference between the rhombus and the parallelogram? Well, I would say that the parallelogram, and I'm going to write the abbreviation here, is a stretched rhombus. Stretched rhombus. So we've taken the rhombus and we've just, let's spell rhombus right. We've just pulled it to make these lines over here longer. Now, how has that changed anything? Well, the angles are still going to be the same if it's a stretched rhombus. So if it's that rhombus that's been stretched, then this angle should still be 110 degrees. And this angle should still be 70 degrees. However, this, where was I going with that thought? I don't even know anymore. Let's draw in the diagonals. Are they going to be the same length? No, they're not. But by stretching it, we've also changed something else. Do you see that the diagonals are no longer 90 degrees? So let's just write a note here, not 90 degrees. Which means that by stretching it, we've changed the angle that the diagonals meet at. So what is the difference between the square and the rectangle? Well, in my opinion, a rectangle is a stretched square. Rectangle is a stretched square. A square has 90-degree angles. A rectangle also has 90-degree angles. A square has sides that are the same length the whole way around. But a rectangle doesn't. This side is equals to that side, and this side over here is equals to that side. How does that change the properties of the diagonals? Well, are the diagonals still equal to each other? If you draw any rectangle, you will find that yes, this side is equals to that side, and this side is equals to that side, so the diagonals are equal to each other and they bisect each other. But did you notice that the angle in the middle is not 90 degrees? So when we stretch a shape, the angle in the middle changes. And when we squash a shape, the angle stays the same, but the angles on the side change. Okay. And also the length of the line stays the same. Let's look at the next one. The next one is a trapezium. Now, whenever I think of trapezium, I always think of a guy in the circus doing his little walk on the tightrope. And why do I think of him? Because he is a trapeze artist. I suppose I should have looked up how to spell trapeze artist, but we'll pretend that's right. Trapeze artist, and he can go on that, he can also go on the swings, but he doesn't work with lines. So no lines in this. And that's why you should not be scared of the trapezium, because there are no lines in a trapezium. Now, the only thing that's interesting about a trapezium is that it has two lines that are parallel to each other. And as you know, any kind of arrow on the line shows us that it's parallel. Now, trapeziums can have all sorts of shapes. They could, as long as they've got two parallel lines, they will be trapeziums. So they could look like that. I don't know what I did there, but we'll go back to our line. They could be this shape in the middle, which is kind of like the one we have already. Or we could pick up and move one of these lines, and they could be like that. They could be like that. They could be all over the place. But a trapezium has two sides that are parallel to each other. Now, this is one that doesn't come up very often. It's properties of a kite. And I know a kite is meant to be one of those things that you fly, and it's got ribbons and stuff like that on it. And it does help to think of it like that. But to be honest, I don't know how many kites still look like this, because mine certainly didn't. When I flew kites, mine were plastic bags tied onto string, and it was great fun. So my kites were not the same. But anyway, let's go into the properties of a kite. I like to think of the kite as two triangles, the top triangle and the bottom triangle. Now, what's interesting about these triangles is that they are isosceles triangles. That side, or that angle, is equals to that angle, and this angle is equals to this angle. Now, obviously, if they meet at the same points, it means that their diagonals are going to bisect each other. Not bisect each other, sorry, That is incorrect. They are going to meet at 90 degrees. But on that note of bisecting each other, this long diagonal does bisect the short diagonal. But the short diagonal does not bisect the long diagonal. Now, the other interesting thing about a kite is that we have angles opposite each other that are equal to each other. If you ever see a kite in an exam paper, it will probably be a congruency question. And of course, we've done quite a lot of congruency, and you should have done a lot of practice. But when you see a kite, you'll probably be looking at some kind of congruency to prove it. So it's good to keep in mind. Now let's go on to the next slide. And this is where we look at our overview. So the overview, basically, we need to discuss what quadrilaterals are. Now, quadrilaterals that have equal sides are either going to be a rhombus, which is a squashed square. So those are the equal sides. Equal angles. Well, we have opposite angles that are equal, and we have all the angles that are equal. The opposite angles that are equal are our parallelograms, and other things. You know what I'm talking about, the rhombus and all sorts. Then our 90-degree angles are the square and the rectangle. The diagonals. It's important to remember how changing the shape will change the diagonals. So a parallelogram will have a short diagonal and a long diagonal, but a rectangle will have diagonals that are the same length. They're both the same. Now, when we bisect angles, like in the kite, it's important to remember that. Can you figure out which other quadrilaterals have diagonals that bisect angles? And the most important characteristic, I think, are the parallel sides. And the reason why it's most important is because it allows us to use properties like alternate angles, corresponding angles, and co-interior angles to prove different things. Co-interior angles. There we go. Okay, but now that we've done all of that theory, and I'm sure your head is spinning right now, we're going to take a look at that practice question. Not the practice question, the challenge question. The point of the challenge question is for you to write it down and then to try it by yourselves, and then we'll go over it, I think in 2 weeks' time when we do preparation for paper 2. So do it in your spare time, get it right, and then when we go over it again, you'll be feeling confident. Okay, let's take a look. The challenge question. ABCD is a parallelogram, that's very important, with diagonal AC. Given that AF equals HC, show that triangle AFD is equals to triangle CHB, and DF is parallel to HB, and DFBH is a parallelogram. Okay, I'm going to give you 2 minutes to write that down, and then we'll talk again. Okay, grade 10s, while you were busy writing that down, I noticed that there is a typing mistake in this question. In A, it should be that triangle AFD is congruent, so that means 3 lines going across to triangle CHB. So make sure you've copied down that error, or copied down the correction, rather. And let's go to the first question of today. Now, given parallelogram ABCD. Now that's really important to note, because if we look at the picture, look, here are our eyes looking at it, where are the characteristics? They're not drawn down there. So it's a good thing that they told us it is a parallelogram. Okay, given parallelogram ABCD with AE and FC, AE bisects angle A and FC bisects angle C. So let's draw this now. Parallelogram ABCD. There's A and B, C and D. Now a parallelogram means that these two sides are parallel to each other and these two sides are parallel to each other. But we also know that AB will have the same length as DC, and AD will have the same length as BC. Okay, then we're told that AE bisects angle A. Here's AE, A's over there and E's down there, which means that this angle over here is cut in half by that line. And FC bisects angle C. So F is over there and C is over there, and this is bisected over here. But what are their measurements? Now the questions say write all interior angles in terms of y and prove that AFCE is a parallelogram. But grade 10s, before we go on and solve this, you need to take a bit of a break from my voice, but you're not going to take a break from maths, because during this break, you're going to attempt to do this by yourselves. Okay, I'll see you just now. Oh, welcome back, grade 10s. I hope you had time to try and figure out the picture. It's actually not that bad when you look at it and you try and figure things out. Now, one of the main problems with doing questions like this is people get all wound up about what kind of reasons they need to write down and where. But the real question is, why are we writing down these reasons? And we write down these reasons because we need to explain where we came to our conclusion, or how we came to our conclusion. It's all very well to say birds can fly. Why are we saying that birds can fly? Well, we're saying birds can fly because they have wings. So what is the reason that we give for our conclusion about birds? Birds have wings, therefore they can fly. So when we're trying to label angles and we're trying to see which ones are equal to y, like in this particular question, then we need to explain why we think they are equal to y. Okay, but then people go, but I don't know the right words to say. Who cares about the right words? At the end of the day, it would be great if you could use the beautiful terminology like supplementary adjacent angles or alternate angles where AB is parallel to CD or something like that. But at the end of the day, your teacher is just trying to see if you understand what you're doing. So if you can't remember in the stress of the moment that the word you're looking for is complementary or co-interior or corresponding, write down the message in your own words and try and explain your reasoning there. That way, at least you've got a chance of getting some of the marks rather than no chance at all. Okay, now let's take a look at how to do this. Now, the first part of the question said, write all interior angles in terms of y. I had a grade 11 recently who got really upset because it was a letter and not a number, and he couldn't get his mind around it. But at the end of the day, the letters are just representations of numbers, and we can write them just as they are. So I'm going to start by drawing in the important information. Firstly, that AB is parallel to CD, and AD is parallel to BC. And the reason why that's important is because parallelograms have certain characteristics. Now, I need to write all interior angles in terms of y. We know that AE bisects angle A, so that means that this angle will also be equal to y. And why is it equals to y? Because the line bisects the two. How do we write this? Well, we start by saying AE bisects. So I'm writing down a whole story, angle A. So there we go. And how do we know this? Because we were told this. So we were given. I'm writing my reasons in brackets. Now, the next thing we need to say is therefore, angle DAE is the same size as angle EAF, which is y. So there we go. That's the first one written down. Now the second one is going to be, let's do that angle over there. Can we do that angle? I'm not sure. Why don't we do this angle instead? Any ideas why I want to do that angle? Because it is an alternate angle. Is it? Sorry, I'm going to do this one over here, because this one is an alternate angle to that. And what shape does alternate angles take? Takes a Z. So let's write it in pink, that FAE is the same size as AED, which is Y. Why? Because they all are alternate angles. And we can't just say alternate angles, we also need to say that AB is parallel to DC. The reason we need to say that is because if we don't, alternate angles aren't necessarily equal. They're only equal if the lines are parallel to each other. Now that means that this over here is 180 degrees minus y minus y. Why is that amount? Because it's interior angles of a triangle. And I'm going to start rushing now and not write it out in the proper way, but I want you to continue writing down the reasons as well as the answers over here, because you need them. Okay, now obviously this is a parallelogram, and we know that parallelogram have opposite sides that are equal to each other. So that means that this, or opposite angles that are equal to each other. So this angle is also equals to 180 degrees minus 2y. And that means that these ones as well are also equal, and this is going to be 2y. But we were also told up here that FC bisects angle C. So that means if this whole thing is equals to 2y, then each one of those sides are equal to y and y. And if angle B is 180 minus 2y, and angle FCB is y, it means that the other angle must also be y. Now, if that's equals to y, then supplementary adjacent angles state that this one over here should be 180 degrees minus y, and this one over here should be 180 degrees minus y as well. Why? Because of supplementary adjacent angles. Now I feel like I've made a real big mess of this, so I'm actually going to go back to the other slide and quickly fill in the details over here so that we can just see what the values are for each. So this one was y because it's bisected. Then this one over here was an alternate angle, and over here we had interior angles of a triangle. Now over here were supplementary adjacent angles, or angles on a straight line, and angle C was equal to angle A because they're a parallelogram, but FC also bisected C, so that meant it was y and y. And angle B had the same value as angle D because they are opposite angles of a parallelogram, which meant using interior angles of a triangle, that was y, and then supplementary adjacent angles would make this side 180 degrees minus y. Shoo-wee, phew. Glad that one's over. Okay, so the next part of the question asked us to prove that part of the shape was a parallelogram. As far as I can see, that's going to be quite easy to do because we've got those measurements in already, or the measurements of the angles. So let's go and take a look at the clean slate. We've got given parallelogram blah blah blah. Prove that AFCE is a parallelogram. So that's this, 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 and this. Now we know that that side is y and that side is y, and this side is 180 minus y, and this side is 180 minus y. Now one of the properties of a parallelogram is that opposite angles have the same size. So if we can prove that they are the same size, which we have previously, then it obviously is a parallelogram. And we would write this like this. We would say AFC, which is that angle, is equals to AEC, which is that angle, is equals to 180 degrees minus y. And why are they equal? Because we proved it earlier. Isn't that a great reason? We proved it. And then we would say the same about these two angles as well. We would say angle FAE is equals to FCE. Why? Because we proved it. Therefore, AFCE is a parallelogram. Okay, I'm going to skip to this next question. In triangle PQR and triangle PSR are equilateral triangles. What does equilateral mean? Equal. So all of the sides are equal to each other. Prove that PQRS is a rhombus. Okay, grade 10s, I'll give you 1 minute to try that on your own. Okay, grade 10s, I hope that went well. And now it's actually quite easy to prove, and you probably doubted yourself while you did it. Obviously, if we have two equilateral triangles that all have the same length of sides and we put them together with the one side sharing, it must mean that they all have the same length as each other. Let me draw what I mean over here. This is an equilateral triangle. Whoa, it's a terrible looking equilateral triangle. Let's do it once more. We'll draw that line first, and that line, then that line. That's the one equilateral triangle. Then we've got the other equilateral triangle at the other end. Now we know that that side is equals to that side and that side. And we know that this side is equals to that side and that side. But now we've brought them together, and in a lovely ceremony, two have become one. Now originally we said that this side was equals to this side, which was equals to this side. But we also said that this side was equals to this side, which was equals to this side. So what does that mean about the measurements of this side and this side? They are the same, they are equal, which makes us happy because it's easy to solve. So let's quickly write that down. PQ is equals to QR is equals to PR, and why? Because the triangle PQR is equilateral. Okay, so then we can say that PS is equals to SR, which is equals to PR. Oh, I'll write RP then. Why? Because triangle PSR is equilateral. And that means, therefore, that PQ is equals to QR, which is equals to PS, which is equals to SR, and therefore the shape is either a square or a rhombus, but it's a rhombus first. Therefore, PQRS is a rhombus. Now, I would explain a little bit more, but we have actually run out of time, grade 10s, and I don't want to keep you away from your other lessons. I want to encourage you to go to your teacher and ask about how they want their reasons written, what kind of terminology and things like that. And make sure that you take proper notes. Now it's almost time for exams, so I hope you've started studying. Over the next 2 weeks we will be doing some exam prep, but it's really important that you do your own preparation. Practice makes perfect, and if you want to be perfect, you need to put that practice in. Enjoy the rest of your day. Goodbye, grade 10s.